So now it's time to give time to our speaker, Professor Jorn Zimmerman from Uppsala University, is quite active in computational geoscience, in particular computational inverse problems, numerical method in general for partial differential equations, and reduced order modeling. Currently, he's an assistant professor at the University of Uppsala in the computational science department. And prior to that, he was a James Van Loo postdoctoral fellow and assistant professor in the Department of Mathematics at the University of Michigan in Ann Arbor. He received his PhD in 2018 from Delft University of Technology. And during his PhD, he spent some time at Schlumberger Research, working on an industrial problem about forward and inverse problem, and one semester at ICERM at Brown University as a visiting graduate student. We're very pleased to have you here, Jorn, for your talk, When Data-Driven Reduced Order Modeling Meets Full Waveform Inversion. I will stop sharing, and you can now share your screen.
Thank you very much for the kind introduction. And yes, today I want to talk to you what happens when data-driven reduced order modeling meets full waveform inversion. Thank you very much first for the invitation to this seminar. So the type of problems I want to talk about are inverse scattering problems. So in an inverse scattering problem, in this sort of sketch here on the right-hand side, we have an array of sources marked X and receivers marked triangle. They will probe a medium, which is in this egg with a question mark in it. And they will probe it with waves. They will penetrate the medium with waves. The waves will scatter up and down in this egg, and some of these waves will return to the array where they will be received. And so these inverse scattering problems are we're trying to figure out what's inside the egg or inside the box without opening it, just from scattered waves that are returned after we send in waves. So an inverse scattering problem is a problem of trying to determine the material from scattered wave behavior. And then in general, the qualitative inverse scattering methods are we're trying to recover the material coefficients of a medium from measured data. These problems are inverse problems. They're typically nonlinear and ill-posed. The ill-posedness here typically doesn't come from the non-uniqueness because if we've measured a material, we're pretty sure it exists. But it comes from small perturbations in your measured data can have a very large effect on the estimated medium. So what type of quantitative inverse problems do we have in geophysics? And I'm talking quantitative inverse scattering problems with waves. For instance, when we try to explore the Earth with towed streamer seismics, typically have a boat with a seismic source towed behind it, which shoots probing pulses into the Earth. These probing pulses will travel into the Earth, reflect up and down, and then there's a long cable with receivers that will receive scattered waves. And from this data, we are trying to make up the material properties of the underlying subsurface. Then also in non-destructive testing, this is used a lot. You can have an array of sources and receivers. If you, for instance, want to know if you have a concrete wall and you're trying to figure out if there's a fracture in it without to see if the structure is sound or not sound. So non-destructive testing also of airplane wings, for instance, these type of methods are used. And then another example that's popular in geoscience is, for instance, trying to, rather than having an active source, like in a towed streamer seismic experiment, using a passive array where we just have receivers, and then we use ambient noise or uncontrolled sources, seismic sources in the Earth that emit waves. And from these passive measurements, we're trying to invert for the makeup of the subsurface. Other quantitative inverse problems in geophysics, where the methods I'll talk about today can be extended or are already extended to these problems, but I won't show examples of them, are, for instance, controlled source electromagnetic imaging or borehole electromagnetics, where we're more in the diffusive regime. So we are using Maxwell and the magnetostatic approximation in order to explore the conductivity of the subsurface, or for instance, if we're somewhere between waves and diffusion in georadar, where we have waves in strongly attenuating media, and we're trying to figure out what's in the subsurface. So these are just a sort of general overview of the type of problems I'm considering. So to get to the problem formulation, I today will be considering the acoustic wave equation with constant density. Since then we have extended these type of methods to also non-constant density problems and to electromagnetics, but for the purpose of this talk, I want to keep it easy on the acoustic wave equation. So we have a second derivative in time, and our differential operator is the wave speed squared times the Laplace operator acting on the pressure. The pressure has a superscript S, which stands for the source location. The source location here at x sub s. We consider it to be a delta function, but it could be anything. And then we have a source wavelet f of t. And we are assuming that current essential initial conditions and homogeneous boundary condition at a faraway boundary that we never reach. And then we can define measurements. So for now, to keep things simple, I will consider coinciding sources and receiver locations. So if you have a source as x sub s, then you will also have a receiver at the same location. So we could just evaluate our pressure, thinking that we could measure pressure for all times larger than 0 at this location x sub x, and we call that our measurement array. So our measurements, this bold-faced D, will be a matrix that's number of sources times number of receivers, which we assume to be square here, and it's a function of time. And this defines what we call the forward map, script F. The forward map maps the velocity, the acoustic velocity, to the measured data. And now the inverse problem is to essentially undo this forward mapping. So that is to estimate the coefficient C from the measured data D of t. This is what we mean when we say we want to solve the inverse problem. What we mean is estimating C from D, and that is finding an approximate inverse of this forward map. The proper inverse may not actually exist. Now, what is a big issue of doing this? The standard approach to solve these problems in full waveform inversion is to minimize data fit. You're measuring data. Why don't we minimize data fit? So this map is nonlinear in general and also ill-posed, but the most straightforward thing you could do is you're trying to invert this data mapping. So let's make a misfit function that is the quadratic data misfit. So the measured data, boldface d of t, minus the forward map f that we can compute of some search velocity v that lives in a search space script c. And then these type of problems, because they're ill-posed for stabilization, always need some form of regularization. This would be the standard approach in FWI, and with a large issue with this objective function is that it is in general not convex. One of the reasons for non-convexity is known as cycle skipping, and this is something that happens even in the most simple cases. And what that means is that you typically need a very good initial guess if you want your method to converge with this objective function. Here I drew a comic to show what cycle skipping is in its easiest form. Let's say we have a source that is marked with an X and a receiver that's marked with a triangle, and we want to estimate what the velocity, constant speed of propagation between these 2 points is. If we do that using this quadratic, data misfit function, essentially if we increase the speed, we see here a red wavelet, sort of the second derivative of a Gaussian in this case, and we see a blue wavelet. The red is what we modeled, and the blue is, the red is what we measured, and the blue is what we modeled. As we increase the speed, the blue wave is going to arrive sooner and sooner and sooner. And so you can think of the speed c, a way to sort of shift the blue wavelet left or right. If you compute the data misfit, which I've done in the top right corner, you will see that as soon as the sort of small negative bumps of the measured and the modeled wavelet overlap, you get a local minima. And essentially here you skipped a cycle. And you will, if you just use convex optimization of this problem, you will get stuck. And you will not be able to estimate the true velocity c that's in between the source and receiver, because the global minimum is unreachable if you will get stuck in this local minimum. And this is sort of one of the big issues. Now, to show this in a bit of a different model setting, I will use this model setting throughout the presentation to also show how other methods would perform this. So the objective function is just the data mismatch. So here I've sort of rewritten this a bit. We have measured data, and this d of t of c is our modeled data. We integrate over time, and this objective function is not convex. So here we have a two-parameter problem. I'm considering a bunch of sources and receivers on the top of the subsurface. We have an angled layer here in yellow that we will shift up and down. That denotes the interface position here given in kilometers. And then we will also consider changing the contrast of that layer. And the contrast here is just essentially the factor, a factor multiplied with the background velocity of 1,500 meters per second. So a contrast of 1 means that the layer has the same speed of propagation as the background near the sources. This is a two-dimensional inverse problem. Let's say we want to know the speed of the layer and we want to know the location of the layer. If we plot the objective function, here I plotted the logarithm of this objective function for a bunch of interface position and for a bunch of contrasts. In the middle, we see the minimum that we would like to achieve, but you can already see that this objective function is quite oscillatory, and you can find many starting locations for which you will not end up in the global minimum because of this cycle skipping. The pulse that we used here is a Gaussian modulated pulse with a 6 hertz center frequency and 4 hertz of bandwidth on either side of the center. So in total, we have access to, let's say, 2 to 10 hertz. And here, the top boundary is absorbing to not have the waves scattering up and down. I will change that in a second. And the cycle skipping is actually a phenomenon that's basically comes from the lack of having low frequency data. We don't have low frequency sources and receivers for these type of problems. If of course, on a computer, I could just simulate what would happen if I had access to way lower frequencies. So let's say we consider this problem and we go down to we cannot measure 0 hertz, but we measure close to 0 hertz and 10 hertz. And if we do that, then we see that all of a sudden there are many starting locations that would lead us to the global minimum. So I'll go back to the band limited case. You see that it's hard to reach the minimum. And if I go to a very broad band pulse, you see that many starting locations will actually get you to the minimum. So cycle skipping is a lack of having access to low frequency data. Then, of course, in reality, the top layer in, for instance, seismics is not absorbing, but actually reflecting, which will make this objective function look quite horrible. So if I add a reflecting top boundary, the waves will bounce up and down between this layer quite often, and you end up with an objective function that looks like this with many, many local minima. So this is horrible to optimize unless you have a very close guess of what this objective function should look like. And now, what I want to spend sort of the first slides on is trying to say we're allowed to dream what would be a good objective function for FWI. Clearly, the data mismatch is not a good objective function. What would a good objective function be? Let's start with sort of the best thing we could hope for. Let's say we're trying to optimize the objective function. We could measure the velocity. This is a bit silly, of course, because if we could measure the velocity, we would have solved the inverse problem. But a nice objective function would be the c minus a modeled c. This is just a quadratic objective function. If we plot it, there's one nice global minima, no oscillations going on whatsoever. But of course, reality hits us here, and we can unfortunately do not have access to this velocity. We cannot be extracted directly from the data in a straightforward way, because that is solving the problem. So perhaps a little bit of a less ideal objective function. Let's consider our acoustic operator, which is c squared times r plus. let's symmetrize it, and I will later explain why we want to symmetrize it, and we consider a Galerkin approximation of this operator on some finite element basis. So we take this operator and we project it on some finite element basis that gives us sort of a finite element operator. So the function here is psi, and if I integrate this operator against each combination of these objective function, I end up with a matrix that's the number of that's exactly the number of basis functions large. And then if I use that objective function, which I call here the ideal objective function number 2, then I have a way of comparing sort of a measured objective function with a modeled finite element approximation. And again, I get an objective function with one global minimum that looks really nice to do convex optimization on. Unfortunately, again, we do not know the finite element discretization of our true operator, so we do not have access to. But this exercise is not fruitless. We actually have access to something that is very close to a finite element discretization of this operator, and that is a reduced order model of this operator. And that's what I want to introduce now. So assume there's a reduced order model space that I'm calling V of X. And this reduced order model space will be orthogonalized snapshot space. Because we have multiple sources and receivers, let's introduce some notation. So let's consider that we consider the pressure wave everywhere in our domain, and we sample it at integer times tau. And then we collect all the wave fields from all the n sub s sources into one row vector. So such that we get sort of rid of the subscript of the sources. Then P sub j would just be the jth time step, sort of the jth snapshot. If you freeze time at j, that's what you would see from all these sources. And then we can assemble all these time steps into a snapshot matrix, and then this snapshot matrix boldface U, which is a function of x, is a row vector field that contains the information from all sources at all integer snapshots of time. There's a type here, this should be n sub t minus 1. And then we will take this space and we will orthogonalize it such that the finite element projection becomes easier. So let's apply a Gram-Schmidt orthogonalization to these snapshots. Then we get a basis V times upper triangular matrix R from our Gram-Schmidt process, which you can also look at as a QR factorization, if you will. And then we obtain orthonormal an orthonormal row vector field V and a block upper tridiagonal matrix R. And then the projection of our PDE, so of our operators C minus C Laplacian Xi, onto these snapshots V of t. We call this our reduced order model, which is now a matrix. And it turns out, even though we do not know the pressure inside our unknown medium, nor do we know the exact operator, C Laplace C, we can actually compute this matrix, which is the projection of this operator onto the basis V from our data. And this A is something that we'll use in a fashion similar to here to do optimization. So if you do that, and of course the rest of the talk will be of how do you compute this thing, but if you actually do a Galerkin approximation of the operator script C onto the special space, the space of orthogonalized snapshots, which is obtainable from measured data, you end up with an objective function that I'm calling script O sub reduced order model. And then if we optimize this distance between the reduced order model that we measure and the reduced order model that we simulate, we get an objective function for our layer case that looks quite nice. It doesn't look as nice as optimizing C minus C, of course, but the important difference is it is obtainable. It has one minima, and you will find it from almost all starting locations. So the claims that I'm making and I'm trying to show in this talk is that reduced order model-based FWI is something that is possible, and essentially that these reduced order models are computable from data The data that I need is I need access to the data at integer time steps of tau, and I need access to the second derivative of this data. I need access to this data from time steps 0 to time steps 2n minus 1. The reason I need access to twice as many data as I have in my space on the last slide is that for the information to travel back to the sources, it takes two trips to a point. So if I want to know what happens with a wave at a travel time n sub t, I need to wait 2n sub t until the information of what happened in that wave comes back to my receivers. And then the claim that I'm making is that this A reduced order model, which is now a composition of two maps, so the map script R, which is the reduced order modeling map, which I will explain what it is later, and the forward map is easier to invert than just inverting the map script F. And so this objective function here is what we'll later in the talk use in order to do optimization. Okay. And then later in the talk, if I have time, I will actually show that you can make a simplification that even the Gram-Schmidt coefficients are defined an objective function that is sort of a modeled the Gram-Schmidt coefficients that we model versus hit from the right with the inverse of the reduced order model coefficients that we measure define an objective function that can be related to matching essentially internal wave fields. But that's later on. So after this introduction, I now want to derive what these reduced order models are and how you get them. And that's sort of the technical part of the presentation for the next 8-9 slides. And then I will go to the numerical results of showing sort of that this objective function indeed outperforms FWI in terms of the quality of images you get. Then if time allows, I'll give some intuition why you could even do this for these Gram-Schmidt coefficients that I introduced and show some results. And then I want to end with some of the challenges we have and sort of an outlook where we want to go with this. So the first thing I will do is symmetrize my partial differential equation. And the reason for doing is that the algebra bar becomes much more tractable and followable in that case. So assume that you know your wave speed c close to your sources, x sub s. Then we do three things to arrive at the symmetrized partial differential equation. So first we do a change of variables. We go from the pressure to the inverse of the wave speed times the pressure. Then we take an even extension in time. So rather than having a quintessential initial conditions until t is 0, we extend time evenly. And then we do a sort of Duhamel-esque transform to transform our source term from the right-hand side to an initial condition. Then we end up with the PDE in this red box over here, where we have the second derivative of time times our symmetrized operator that I talked about before, which is minus c Laplacian c, acting on fields u that have an initial condition at time 0 that we call b, and a time derivative because we have the even extension is equal to 0. Then also to sort of simplify this notation with all these sources that we have going on, we're going to collect all the sources from 1 to n sub s in a row vector field that's boldface u, and then we essentially have a single PDE to cover all sources. Now, the solution of this PDE is now quite simple because we have an even extension in time, and we have homogeneous boundary condition, and A is positive definite. We can define functions of this operator via its spectral decomposition, and the solution just becomes the cosine of time times the square root of this operator acting on your initial condition B. And you can show that the data, which is the pressure at a single point, can be expressed in a symmetric fashion. So essentially you can define the inner product with your source functions because we assume coinciding sources and receivers. You can define the inner product with the source functions on these fields u as your data. And these are, you can relate this data to the data you measure. Then what are these B's, you might ask? So, there's a typo here. B is a row vector field that goes from 1 to n sub s and not m. It's a row vector field that is supported near the sources, and you can show that when you do all of these symmetrizations that it's essentially the Fourier transform of your wavelets, the square root of that acting on the square root of the operator acting on a delta function at a certain source location x sub s. These functions are computable, and they are sort of source functions that are localized around the source, and they are in order to transfer this to more of a dynamic systems-based approach. Then f hat is the Fourier transform, and in this case, because we have an even transform in time, we assume that the pulse is even. If your pulse is not even, you can just convolve with the time-reversed variant of your pulse and do a pulse compression, and then you have effectively an even pulse. So why do I do all of this symmetrization is that all the algebra will be much easier because our Green's function is now a cosine of an operator, and our operator is symmetric. And also our data acquisition is symmetric. So we have source functions B that are also receiver functions B. And essentially, we've split the source half over the source, half over the receiver, which is the reason you have a square root act on the Fourier transform of f. Okay, so now that I have this, what can I do with this? I want to make a reduced order model of this, which typically means I want to approximate my field U in some sort of space. I've already hinted at what this space is, so the space will be the snapshots. So similar as we did before with the pressure, I will define U sub j as the field U at discrete time step j times tau, and then I will collect all of these snapshots inside a row vector field U. And then I want to approximate my field U of t in x in this finite dimensional snapshot of a subspace of snapshots. And this approximation, of course, is very good as long as you're within sort of the time span where you have snapshots. And so then you can make an approximation that we call U sub g here, so the Galerkin approximation, which then is essentially a separating time and space here. Is this row vector field U multiplying times a time-dependent vector G, and G then has the size of number of time steps times number of sources times number of sources. And that this is a Galerkin approximation. The Galerkin condition then is that the error you make, so the difference between U sub G and U, multiplied with the PDE operator, is orthogonal to your space. So that's the Galerkin condition. And if you do that, you end up with two matrices. You end up with something that's called the mass matrix, which is the Gramian of the inner product of U with itself. So that's every field U at every time step, inner product with every field U at every other time step. That's in front of this function G double prime. And then you have the projection of A onto this finite dimensional space U, and you have some initial condition. So M is the mass matrix, and S here is the stiffness matrix. And if you do a Bloch-Cholesky factorization of this mass matrix is a Gramian and positive definite. If the basis vectors U are linearly independent, then it defines an orthogonalization of that space as U is equal to V times R, and V then is this orthogonalized basis. So you could equivalently do a Galerkin approximation of this in this orthogonalized space. And this V here is a very important function. It has many nice properties. It turns out that, first of all, it's localized. Then it is causal, and I'll explain what that means later. Essentially, because R is an upper triangular matrix, and you do this via Gram-Schmidt factorization, let's say the fifth vector in V is a linear combination of the first 5 vectors of U. And what that means is that sort of the travel time the travel time hull of the functions of U, V is also supported in sort of that travel time domain. So the functions V's obey causality, and that they have the same, that they are only supported where in the travel time cone of U. And more importantly, it turns out that this orthogonalization process gets rid of some of the dependence of C. So it turns out that these V's are only weakly dependent on C, and for certain materials we actually have proofs, and we can show that this is the case. That they have a weak dependence on C, and to be more specific, they are weakly dependent on the scattering part of C and strongly dependent on the kinematics, of course, because the kinematics of C, how a wave propagates, determines the travel time cone. And now the important thing is that, and I will show this, is that these matrices M and S can be purely obtained from the data samples and the second derivatives without knowledge of this space U. We do not know the solutions inside our unknown medium. If we knew, it would be much easier to get our unknown coefficient C. So if instead of projecting onto our non-orthogonalized space U, we project onto our orthogonalized space V, we would end up with the following reduced order model, where we have sort of U Rho is now the reduced order model variable. The second derivative in time of that is equal to sort of this reduced order model operator A, which is a matrix acting on the field. And you also have initial conditions for U Rho. And now this A Rho, so the boldface A superscript Rho, is the Galerkin approximation of our continuous continuous space operator script A projected onto these snapshots V. And I've already shown that this leads to nice properties, but here is where the reduced order model comes into play. Now I want to briefly show that you can actually get these mass and stiffness matrices without any knowledge of U whatsoever. So if you consider the ijth element in the mass matrix U, that's the ijth element of the Gramian, which is just the inner product of U at time step I with U at time step j. Then it turns out that these can be purely computed from the data, even though U is unknown. And because we sort of symmetrized our equation, this is quite easy to show. So U at time step I is nothing but the cosine at I times tau times the square root of the operator. And U at time step j is just the cosine of j times tau times the square root of the operator. Now, in this inner product, the operator is symmetric, so we can just shift the cosine of this operator to the right-hand side. And then remember that if we multiply two cosines, that's equivalent to taking the sum of the difference of the argument and the sum of the argument. So if we take the product of two cosines, we get the sum and the difference of the argument. And then we can realize that the sum and the difference of the argument are the field exactly at time step I plus j and at time step I minus j. And because we took an even extension in time, we've got an absolute value about I minus j. And then this inner product just collapses to the data at time step I plus j plus the data at time step I minus j. And this is now essentially M, you can see, is sort of the data at time steps at various time steps. And so M is a Hankel matrix plus a Toeplitz matrix indeed. And then for the similar formula you can derive for the stiffness matrix, you can sort of already feel that this operator is nothing but a second derivative due to our PDE. So all that happens is that you get a Hankel plus Toeplitz matrix of the second derivative of the data. And so we get Hankel plus Toeplitz structures for M and for S. And so these are data-driven reduced order models because we can get the projections we can compute the Gramian and the projection of the stiffness of the operator on U, the stiffness matrix, purely from the data. And now to orthogonalize them, we just use the Cholesky factorization, or because we have all these block structure with a number of sources, the block Cholesky factorization. And if we take our space U and we hit it from the right with the inverse of R, we get orthogonalized snapshots. And these are causal, meaning that V at the time step J is only a linear combination of all U's up to that time step J. And it turns out that these V's are strongly, and I will show that in some pictures, dependent on the kinematics and weakly dependent on the variations in the waves-to-see that come from scattering. And they're also localized at the wavefront of the associated time step. So you can interpret this as sort of a not good finite element basis, but sort of a locally supported function like you would find in finite elements. So I want to show you how these functions look like. Here's an example. I have 50 sources and receivers above some buried slanted inclusions. I'm using a Gaussian modulated pulse to excite this. And here I have a cutout of this configuration of these slanted inclusions. And in this cutout, I will show you how U looks. So U is at the bottom left of the page. And you see that there's sort of a spherical wave, and that spherical wave has some scattering events at these slanted inclusions. And then also, after orthogonalization, you end up with one dark red spot, which is exactly this focal point I was talking about, supported at the wavefront. And you may then ask, why would this Rome misfit actually work? So it's essentially either a local averaging of your operator, and as I've already shown, that a true finite element approximation of this operator leads to a good objective function. Here, essentially, we use these V functions rather than a finite element basis, because this gives us a computable misfit function. And then if to show that they're indeed only dependent on the kinematics, here I computed the U in a constant background medium that has sort of the same constant background as my true velocity, and I truly only have a spherical wave. If I do this orthogonalization process there, I end up with a very similar function V, which I call V0 here. And indeed, then this just to show that you have a strong dependence on the kinematics of the medium and a weak dependence on the scattering of the medium. Okay, so now that we have the reduced order model there and we're through sort of the technical slides, how do we do inversion with this reduced order model? So we claim that the composition of the map F, script F with script R, which gives us the reduced order model, is easier to invert than the data. So we have our data, we construct a mass and stiffness matrix, then we do a Cholesky factorization, and then to get our reduced order model A, we hit the stiffness matrix on the left and the right with our Cholesky factors. And these reduced order models are large. They are larger than the data, which we do something about in 1 second. But what we will do is we'll minimize the reduced order model misfit. So rather than the data misfit, we are going to reduce the misfit of A Rome minus the composition of the map script R with script F. And then here I've written this truncation operator in front of it. Because A Rome, we essentially made the data larger. We made the data t times larger than it originally was. We truncate this reduced order model, since we can show that most of the information lives close to the diagonal, and this truncation operator essentially only takes the first few blocks of this operator in order to sort of reduce the dimension, and then we do a Gauss-Newton optimization approach on this objective function. For that, we need to compute Jacobians, and you don't want to store that large Jacobian, so that's why we truncate that. And then we add a bit of this layer stripping approach, where we first feed in the first time measurements, which gives us a small reduced order model, and we optimize the medium close to the array. And that's because these reduced order models are strongly dependent on the kinematics, and we hope that way, in a layer stripping fashion, we get the kinematics right, and we get a fastly convergent method for inverse problems. So the first convexity test, now to the numerical examples. The first thing we did is we cannot prove convexity, but we can resort to numerical experiments. So in this layer that can shift up and down, and you can change the contrast of the layer that I used. If we just go for the FWI objective function, there's many local minima, and if we look at the Romus function, there's one global minima that's obtainable from almost all starting locations. So that sort of gave us hope, and we started doing test problems. One test problem that's in the sort of FWI community that's quite popular is the Camembert test problem. So you have a Camembert cheese with a fuse with 10 sources and receivers above. Again, we have a center frequency of 6 Hertz and 4 Hertz on either side of it, so of bandwidth. And then we add a bit of Tikhonov regularization, where the regularization parameter is dependent on the singular values of the Hessian, of the approximate Hessian, so the Jacobian transpose to Jacobian. And then as a search base for our velocities, we use some Gauss's basis functions, where the range and the cross range section of these Gaussian basis functions are locally supported, and the range and cross-range width are dependent on the resolution that we would expect. And then we do a bit of layer stripping. So we start with the first times and start sort of from the top and optimize to the bottom. If we do that for the reduced order model and for FWI, we slowly feed in more and more data. The reduced order models get larger. This is in order to prevent that we get stuck in some local minima because we don't know the kinematics very well. We see that on the top row that the reduced order model converges and fills out this entire cheese, the entire circle, and FWI, of course, gets the first reflections are easy to match, so getting the top boundary is not a problem, but very quickly you get stuck in a local minima and you fail to fill out. So if there's only one thing you take home from this talk, then it is that the reduced order model will give you more cheese, and this is the main message. But let's go on to some more difficult problems. Another test problem many people like to use is the Marmursi problem. So we're looking at the Marmursi problem with 30 sources and receivers, and again, the same type of modulated pulse. We again use exactly the same Tikhonov regularization for reduced order model and FWI. To make it a bit harder, we add 1% noise on our data, and then we do optimization in this layer stripping fashion. So here we divide the medium up into 6 layers and feed the data that would have seen these 6 layers in one after the other. And our initial guess here is just a linear gradient in depth, as is common because you're not sensitive to these low variations unless you have very far offsets and have access to diving waves. So then after 6 iterations, FWI and the reduced order model sort of look very, very similar, and you cannot really see any difference between the methods. But then as you go deeper and deeper and iterate more and more, the reduced order model gets an edge over the FWI that gets stuck in a local minimum. And especially in the middle of the image, there are a couple of fast inclusion that the reduced order model is able to fill out, and FWI just with the same regularization fails to. Of course, you could add fancy regularization schemes that would help FWI out here. Then in seismics, you do not have full array data. So one critique we got on our work was that we require full array access. So in order to sort of look into that, we considered a towed streamer setup where you can assume that you essentially measure the whole array except for a source cannot act as a receiver. So we're missing the diagonal of our data matrix. And then we try to resolve this. So first we have some interpolation routines and some data pre-processing to recover an approximate diagonal of our data, and then we run all of our machinery to make this work as good as the previous case. We needed to sample slightly finer in space, and we were able to also recover the Marmursi test. And now, sort of to the nicest example, in my opinion, that we have is we thought, how far can we go with this? So we tried to do something that's called time reversal in random media. So on the left, you see smooth random medium. The random medium has Gaussian statistics and Gaussian covariance, and the fluctuations are around the reference velocity that is known, and they are on a scale that one cannot resolve with the pulses that we've used. It's highly scattering as well. And the time reversal experiment is essentially that you would like to focus inside this unknown medium at a certain depth. And you would like to find the source function that you need to apply at the sources and receivers that would focus at a certain depth. And due to the symmetry of the wave function and reciprocity, what this is just it's the time reverse screens function that you should supply on the sources in order to reach a certain point and focus at this point. But the time reverse screens function is unknown. The Green's function is unknown because the medium is unknown. So idea is to first use our reduced order model approach to reconstruct an approximation of this random medium, and then calculate this time reversal in this random medium to see how good our approximation of this random medium is. So here's our reconstruction of 135 iterations of the Gauss-Newton iteration, and it's of course I will go back and forth between these slides. A bit difficult to see if we did a good or a bad job. But in general, if you stare at it long enough, you can see that there are fast inclusion in our random medium when they're fast inclusion in a true random medium. And the correlation, if you compute the spatial correlation, is just 61%. But the random medium is beyond the resolution image, and of course, further away from the array, you're also losing resolution in cross range. So we do a time reversal experiment to check the quality of this reconstruction. So let's try to focus at a given depth here, and we do a time reversal experiment. And the results are on this slide. So on the left is if, as our Green's function that we use to focus at a certain point, we use the Green's function of the background, C sub 0. Then our focusing is as good. On the left, you can see there's many energy outside the black circle where we try to focus. And the energy is spread throughout. Now, if we take the solution from our reduced order model inversion, the energy inside the circle is much higher, as you can see from the color scale that's now cropped a little bit, and there's less energy outside of the circle. Of course, if you had access to the true medium, you could focus much better. So if you have the true C and you compute the Green's function, then you would have a very tight focus inside the circle. But we are very happy that this reduced order model is able to capture the oscillations in the random medium well enough to do some time reversal experiments. Okay, so some conclusions on this reduced order model misfit. So our objective function is more convex than just using data fit, and we can get rid of many of the cycle skipping problems FWI had. Of course, we are adding a layer of complexity because we need to compute these reduced order models. And if you don't use the Hankel plus Tuplet structure, the number of computations scales as the power 3 of sources and time. However, in our experiments, the computation of Jacobians and gradients are much more expensive than that. So we still think that this is a viable options for small examples right now. The other thing that I've hinted at, and I want to spend five minutes on, is this reduced order model. We've now just used it to optimize the dynamical system, but could we actually approximate internal states with it? So I've said that these basis functions they are not, you don't know them inside your unknown medium, and you also don't know V inside your unknown medium, the orthogonalized snapshots. But R are the Cholesky factors of the mass matrix, and they're obtainable purely from data. But I've said that V sort of only depend on the kinematics, and the scattering effects are, if you will, orthogonalized out. So could we approximate these internal states even though we don't know the medium? And the answer of that is positive. So if you know a smooth reference velocity, which you could get from essentially, for instance, doing an inversion, but if you know a smooth reference velocity that has roughly the same kinematics, then the orthogonalized snapshots in this reference field are the same as the ones are close to the true snapshots that you don't know. In layered media and waveguides, we can actually bound this error and show that it is small, but in general cases, we're still working on trying to show this, and it's in general very hard to show that these are close. But if you do this and you just replace these V's, which you don't know, with V's in a reference medium, you can use this to estimate the internal Green's function. And in essence, what you're saying is that V depends on the kinematics of the medium, which are unknown, and R depends on the scattering. So you can capture the scattering of a medium, but not the kinematics correctly if you approximate these internal states. So to show this, what I'll do is I will show this estimated internal Green's functions. So U can be decomposed into V and R. And if I want to know the Green's function to all my sources for all time steps at the point Xi, then all I have to do is I have to evaluate V at Xi and hit it from the right with my Cholesky factors R and the canonical basis vectors E, J. And then I can, this quantity is of course exact, but if I replace V with some reference velocity, and this is a good approximation, I could approximate internal Green's functions. To show this, an easy example where I actually know the kinematics is just I have a very thin ellipse here that is fast inclusion. It's 3 kilometers per second, and the background is 1 kilometer per second. In case the wave from this internal point will travel directly to the sources, and then it will scatter from the left and the right side of this ellipse to all the sources and receivers. And those are the events A, the direct arrival, B, the reflection from one of the sides of the ellipse, C, the reflection of the other side of the ellipse. And now I've marked these events A, B, and C. If I compute the true internal Green's function, then with the wavelet used to image this, I clearly see these 3 marks. And now if I use my reduced order model and just replace the V's that I don't know with the V's in the reference medium, I get the seismogram on the right. So on the y-axis, you see the time steps starting from 0 up the top all the way going down. And these parabolas are essentially the direct arrival and then the first scattering events. And on the x-axis, you see the sensor index that senses the function. So the Green's function here goes from the sources, 40 of them, to this internal redly marked point. And you see that we can indeed approximate the internal functions because there's no kinematic effect. There's only scattering effects. And these dashed lines, they line up very well with the events in this data. If I now make this ellipse thicker and give it a kinematic effect, which I've done here, you will see that we still approximate the scattering events B and C very well in our reduced order model, but the kinematics is off. So if you look at the top dashed line, you see that in the background, the 0 point between the blue and the red wave is exactly at the dashed line. In the reduced order model, that's also exactly the case. The 0 between the red and the blue is exactly at the dashed line. But for the true wave speeds up inside this ellipse, which now is thick enough to have a kinematic effect. And we see that the red maximum is actually exactly where the dashed line is. So I will go back one more time, and you'll see that here the kinematics are correctly approximated, and then here the true wave arrives much earlier. However, the reduced order model fails to realize it because I've used a constant background with essentially the wrong kinematics to approximate this. And then due to time, I will skip this slide. But what you can essentially do is you can show that you could, rather than optimizing the reduced order model, the projection of your operator onto the space V, you could optimize for internal solutions. So you can make an objective function that's the difference in internal solutions by taking the difference of the reduced order model with a measured, so the Gram-Schmidt coefficients with the measured Gram-Schmidt coefficients. And if you do that, you can get an objective functions that's performing as well as the reduced order model objective function. So here we have the BP salt model with a thick salt layer, which is hard. It's hard because the Camembert problem also was hard. It's a large, fast inclusion. And if you don't do a good job of regularizing, if you just use Tikhonov regularization, FWI will only get the top of this salt inclusion. However, by matching internal solutions with a reduced order model or using the operator ROM, you capture the main features. And the reason we also like this objective function of matching R's is that if you only match R's, it turns out that it's a bit more stable with respect to perturbations, to noise, and easier to compute because R only depends on the data and not the derivatives of data. There are, of course, other people that have approaches to avoid cycle skipping in FWI. So one of the things is that typically what people do is they try to go from low to high frequencies in order to avoid putting objects into the inversion domain that are very sharp. So you go from large features to smaller features to avoid local minima. Then there's, of course, people that do layer stripping, which we use here as well to use the causality of wave propagation to avoid getting stuck in local minima. And then another popular approach nowadays is from Enquist is the Wasserstein distance or the earth mover distance. So rather than taking the L2 norm of the data mismatch, you could use the Wasserstein distance, so the Earth mover distance. So how far do I have to shift if you would like the measured signals from one to the other. And the Earth mover, we have some examples where the Wasserstein distance doesn't perform as well as our reduced order model, but to illustrate this, for our simple one-layer example, the Wasserstein distance actually has a very desirable objective function. Now, the challenges we have is essentially that we've extended this framework now to 2-parameter inversions to actually be able to do real acoustics and not just a wave equation, so to invert for rho and c. We've extended it to anisotropic magnetics, but other things we would like to do is we would like to include absorption. And of course, FWI is nice because all you need to do is you need to be able to simulate the PDE, and you can optimize for medium parameters that would fit that. But here, every time we have a new equation, we essentially need to custom tailor a reduced order model that has desirable properties. So something we want to do is we would like to do viscoacoustic or the full Maxwell equations with losses, and we're working on that. From a computational side, we would like to look more at fast computational linear algebra to do a fast Cholesky factorization of Hankel matrices in general, or Hankel plus Tuplitsch matrices. And right now we are computing the Jacobian explicitly using finite differences, but we're currently working on adjoint state models in order to get faster Jacobians like you would do in normal FWI. Now, there's other people that also work on this for diffusion problems and internal solutions, notably Vladimir, Shari, and Michael. And I listed some references here, but also for the wave equation in the frequency domain. Andreas and Tristan are working on these type of things. And so to wrap this talk up, I would like to thank you for your attention. And my conclusions are so that these reduced order models can make well-behaved objective functions, and then also that even though we don't know the space U and we don't know the true operator, we can still get these reduced order models from data. And here are the references of that I used to make this presentation. I'd like to acknowledge and thank my collaborators, Liliana Borchea, Alexander Mamonov, and Jocelyn, and also the computational support at Uppsala from NICE and UPMAX. And with that, I would like to conclude my talk. Thank you so much for having me.
Thank you. Very interesting. I have a few questions. First of all, you showed examples mainly in 2D. Do you expect major difficulties in moving to a three-dimensional situation?
We are working on that, and I think it's mainly a computational, like we need to scale computations. We already have the formulation in sort of blocks, which with the blocks are the size of the sources. The only thing that changes when you go to 3D is that you don't have a linear array, you have a two-dimensional array, and the formulation still works. We've written it all up how it would work in 3D, but we first want to focus on making our computations in 2D more efficient. So we would like to have a joint state method to compute Jacobians before moving to 3D. But we are working on 3D, and I am excited for those results. But right now we need to make 2D more efficient.
So hi there, sorry for joining in a little bit late. I got stuck on a personal matter. So I actually had a similar question. So to complexity in 3D is there's always more complexity and you need more time to solve.
Yeah.
No news. But so even with 3D, it's my feeling that you would have more of these local minima that you would get stuck in because of the reflections get more complex in 3D, and that would not affect your solutions?
I mean, for that, of course, we we need to see what happens. Of course, in 3D,
Right.
the problem is computationally harder, and also there's more local minima for FWI. For our objective function, we don't know. We will start with no longer the camembert problem, but the soccer ball problem, and then
cheese can
sort
be
of see-
three-dimensional, no problem.
Yeah, that's true.
Camembert is in
That-
3D,
yeah.
yeah.
True one is, yeah. So that's sort of the steps we need to do. But we're just saying that conceptually there's nothing in 3D that doesn't work. Of course, the sources get more, and computationally things scale worse. And that's why right now we want to this adjoint state method, and we want faster linear algebra, because right now we just compute the general Cholesky factorization of these Hankel plus. We just use the normal routine, let's say, of Hankel plus Toeplitz. We've already and we think that using Fourier transforms and methods like that, we can do that much faster than the true complexity. And so that's why we're first sort of want to nail the linear algebra down. The past year, we've worked a lot on stability with respect to noise that I haven't touched upon, but if you get noise, essentially this mass matrix is numerically if the mass matrix is no longer positive definite, so you need to sort of stabilize it, and that's sort of the stage where we at right now. But we do want to go to 3D, to more different types of physics, and I would say there's many open things to go from after sort of establishing that this can be done.
I'm just wondering if your way of building the objective function through the reduced model can be seen as in fact, as a new metric on the data. I don't know. It's just
yeah.
I'm just trying to understand better
what it is. Yeah.
Or putting it in a frame that I understand better. It's just.
Yeah. So we call it
sense.
this. We call it the script R transform. But I mean, you take data and it's a map of the data, and you can take derivatives of that map. We can study that reduced order model map. So you can understand it as, I guess for a metric, you would also need to look at, I mean, definite is not an issue, but at distances in that map. But that's interesting. Of course, if these V's, these orthogonalized basis functions, if we could prove that they were independent of C, then this whole study this study becomes more easy, and then we can show things. But bounding the difference between these V's is a bit difficult, because in the objective function you have your A, which is your operator projected on the V's that belong to the true C, and of course the V's that belong to the current iterate C, and that's what you use to project sort of the reduced order model of your current iterate. So these projection spaces are varying with C slightly, and that's what has sort of impaired our analysis. So we have something in waveguides in order to get a grip on it, and we are trying hard to prove these things. But for the rigorous stuff, we sort of a bit hampered by these projection matrices not being constant, because if they were you could show that they're like finite element type, then you have all this machinery to available.
Just a final question that is just I don't know if it is a provocative question anyway, just a curiosity, just want to know your opinion. At the moment, there is a lot of activity on the use of deep learning neural networks for inverse problem. Do you think for the type of problem you're treating here can be of any advantage? Do you think they can give some or let's say more traditional, just between quotes, reduced basis model like yours, because more or less the technique falls into the, let's say, category of reduced basis is more than sufficient for your class of problem?
For the class of problems, I think learning and deep learning definitely has its space. For physics, I think we have very good methods for computational physics, for forward problems. We can prove many things, and there are people working on also making the deep learning approaches more rigorous. But I see in these type of problems right now for deep learning, I more see things like building regularizations or ways where we don't have a mathematical way of including them in our objective function. That's where I see sort of this deep learning coming in. I feel like on reduced order models, we have a grip. We can sort of, it's not some black box stuff. We have a grip on a lot of things. Also the computational physics forward problems, we can show and prove a lot of things. So I'm skeptical that there is these model deep learning can outperform anything. But for regularizations, for instance, I would see that when we essentially want to say we're looking for objects that have this type of form, that you cannot make a mathematical form model what you mean by I'm looking for this type of objects. But you could use deep learning to essentially post-process, but also to make a regularizer that says, oh, the object you have looks like something I'm looking for. So that's where I'm seeing advantages right now personally. But yeah, I agree there's much activity in that field.